Hey, this is Mr. Woodward. In this video, we're going to talk about a new concept called net force. Okay, we've learned about forces before, but what is a net force? Well, the net force on an object is the sum of all the forces acting on it. So if you have the value of a force in pounds or newtons, you can essentially add up all those forces to come up with the net force. Okay, when the net force equals zero, meaning that the sum of all the forces is zero, we can say that an object is in equilibrium. And if it's in equilibrium, it's either going to be in one of two states, either staying at rest, because all the forces on it are balanced, the net force is zero, or it will be moving at constant speed in a straight line, okay? So, first of all, in physics, we usually use the unit of force called the Newton. Okay, and 1 Newton is roughly equal to 0.2 pounds of force. Okay, so let's take a look at a couple of examples of how we can look at the forces that are acting on an object and then determine the net force. So let's look at this first example. We've got 5 newtons to the right and 10 newtons to the right pushing on this object. And so the net force on them would be 5 plus 10, 15 newtons to the right. Okay, you just add them up. In other words, the net force is like a single force that could replace all of the applied forces. Let's look at the next example. Well, what if you have 10 newtons to the right and 5 newtons to the left? Well, this one you could think of as like positive 10. This one you could think of as like negative 5. And so when you add them up, 10 plus negative 5 is positive 5. So those forces could be replaced by a single force of 5 newtons to the right. And then in the last example, what if you have 5 to the right? You could think of that as positive 5, and 5 to the left, you can think of that as negative 5. Well, they would add up to a net force of 0. Okay? So these are examples of the net force in the horizontal direction. You could do the same thing in the vertical direction. So what if you had, the same mass, but now you have 2 forces maybe vertically? So maybe you've got 7 newtons down and you've got 6 newtons up. Well, then that would be equal to a net force of 1 Newton down, right? Or maybe you've got 10 newtons down and 12 newtons up. Well, that would be equal to a net force of 2 newtons up, okay? And then, of course, if you've got maybe balanced, right? 5 newtons on both. That would be equal to a net force of, as they wrote up here, 0 newtons. Now, if you start looking at examples where maybe you have forces in both directions, let's say you've got something like this. You've got an object with horizontal and vertical forces at the same time. Then you can actually separate the directions, and you could talk about, well, what's the net force in the horizontal direction versus the net force in the vertical direction. So oftentimes, though, you'll only get maybe one of them going on. So here's an example. So the net force in the vertical direction is going to be equal to 0, right? Because you've got 10 up and 10 down. But the net force in the horizontal direction is equal to 2 newtons to the right, okay? And so oftentimes for a situation like this, you could just replace the whole thing by a diagram like this, showing just the single 2 newtons to the right as the net force of all of those. So let's take a look at a few more specific examples of how we can use net force. So here's 3 examples. Example 1, a 450 Newton chandelier hangs at rest from a ceiling by a chain. Consider the forces acting on the chandelier. So let's say my chandelier is kind of like this. It's usually hanging by a chain, right? So if these are the chains, I want to erase those chains and replace them with the force that acts on them. So first of all, the chandelier is going to experience a force of gravity down. and it's going to experience tension from those chains supporting it. Okay? It says it's a 450 Newton chandelier. This is describing its weight, which is the force of gravity on the object. And then if it is at rest, then the net force must equal 0, right? So I can say this over here. The net force is going to be 0 newtons, which means that the tension must be 450 newtons as well. Now it's in a state of equilibrium. What about example 2? Now a 36 Newton bowling ball rolls down a bowling lane at a low constant speed without friction. Consider the forces acting on the bowling ball. So here's my bowling ball. Right, usually rolling down a bowling lane, but I'm going to erase that bowling lane and I'm going to replace it with the forces that it puts on it. So the bowling lane is going to act upwards with a normal force. That will be counteracting the force of gravity downwards. And then it says it's without friction, so I can ignore that. And it says it's a low constant speed. So at low speeds, there's not noticeable air resistance. So this is it. If it's a 36 Newton bowling ball, that's describing the weight or the force of gravity. And the bowling ball, as it goes down the lane, it doesn't accelerate upwards or downwards, so it will be vertically balanced, right? And so in this case, the net force is also going to be 0 newtons again, okay? And as I stated in the previous slide, the net force is 0 in these two instances, right? The first instance is when an object is at rest, the net force is 0. In the second instance, when an object is moving at constant speed, the net force is 0. Those will always be true, and those are the only two instances when the net force is 0. Okay, but what about an example where the net force is not 0? Let's take a look at example 3 here. An 8 Newton toy car accelerates on a track. Okay, so now we're accelerating. This is different. It's pulled by a string with a force of 2 newtons to the right and experiences 1 Newton of air resistance. Consider the forces acting on the car. All right, so I'm going to draw my toy car here. Okay, it says it's an 8 Newton toy car. That must be the force of gravity on it. And it's pulled to the right by a string. So that must be the force of tension, right? And it tells me it's 2 newtons. It experiences 1 Newton of air resistance. Well, if the car is accelerating to the right, air resistance always opposes that. So I would expect this to be to the left. 1 Newton, right? And then there's the track as well below that's supporting it. So that's going to be a normal force upwards. Now, if it's a level track and the car is only accelerating to the right, then it is going to be balanced vertically, meaning the forces in the vertical direction are going to balance each other. So I can safely say that this normal force is equal to the force of gravity. It's also 8 newtons. So the sum of the forces in the vertical direction are going to be 0, meaning the net force in the vertical direction is 0, but there is an unbalance of forces in the horizontal direction. I've got 2 to the right, and I've got 1 Newton to the left. So the net force is going to be 1 Newton to the right, because I've got the 2 here and the 1 here. You can think of that as -1. It's in the negative direction. And so 2 minus 1, positive 1 Newton to the right. All right, so this has been an introduction to net force and a few examples of how to calculate the net force on an object.